Hi, this is Ron Sipsic. In this particular segment, we're going to take a look at something called the time value of money. The reason we're looking at the time value of money is we're going to take a look at what we call investment decision making. And investment decision making has to do with incurring costs in the present, but those returns not coming back until the future. And to understand how to compare future returns to present costs, we must first understand the time value of money. So that's what we're doing here. One of the most important ideas to know in finance is the idea that a dollar today does not equal a dollar tomorrow. In other words, a dollar in hand today is more valuable to people than a dollar in hand a year from now, 10 years from now, or 1,000 years from now. And it's a very simple idea. It has to do with the concept of opportunity cost, in that having a dollar today and being able to spend it today and enjoy the value of that dollar today, that is more valuable than the pleasure being delayed. In other words, having the dollar in the future, being able to spend it in the future and get the value or the pleasure in the future. So pleasure in the present is more valuable than pleasure in the future. It's a simple opportunity cost idea that I'd always prefer to be able to spend the dollar today than to have to wait and spend it in the future. Now, if you want to look at how to equate a dollar in the present with a dollar in the future, you have to incorporate something called an interest rate. So let's do an example here. Let's say, for instance, that you have $100 today, $100 today, and if you have it today, this is called a present value, PV, present value. If you multiply that present value by something called the interest rate factor, and let's just say, for the sake of argument, that the interest rate today is 3%. We'll talk more about interest rates in just a minute. But let's say the interest rate is 3%. So if you take that $100 today and you multiply it by 1.03, you're going to get a future value of $103. So the point is, if the interest rate equals 3%, then $100 today equals $103, let's say, a year from now. Let's say the interest rate is 3% for a year. So while a dollar today does not equal a dollar 1 year from now, if that's true, then $100 today does not equal $100 a year from now, but $100 today equals $103 a year from now if the going interest rate is 3%. Now, it's very interesting to study the whole idea of interest rates. An interest rate is really compensation. Let's just write this out. The interest rate is compensation for three things. So let's identify why people are paid interest, okay? And apologize for my writing. It's not very good today, but bear with me. So the interest rate is compensation for three things. One, it's compensation for what we call the opportunity cost. The opportunity cost of foregone value. And this is what I was talking about earlier. You must pay someone to give up the right to enjoy value today. So if I have a dollar or $100 in hand today, I can buy something worth $100 of value or more. But if I don't have that $100, if I've loaned it to someone, I've given up the right to spend it today, which means I have given up having value today. I have to wait and have value in the future. That's an opportunity cost. Okay? So one reason you have to pay someone interest is you have to compensate them for giving up value they could enjoy today. A second reason that you have to build in interest is for something called inflation. There's got to be a compensation for inflation. So inflation is a loss of purchasing power, involves a loss of purchasing power. So when there's inflation, prices are rising and purchasing power is falling. So during inflationary periods, you have a loss of purchasing power. And if you're going to lend somebody money, you're going to be repaid in dollars that are less valuable. So when you lend, lenders lose purchasing power, and they have to be compensated for that. And that's going to be built into the interest rate. Now, let me just give you a simple, very quick, simple example here. So let's say that I want to earn an interest rate from you of 3%. I want to be paid 3%. So I stands for interest rate. There's two things that are going to go into building that interest rate. One is the real interest rate, what I really want, what I want to be compensated. I want to be compensated, let's say 2%. This is called the real interest rate, R. I want to be compensated 2% for having to give up value today and having to wait and get it in the future. But let's say that I also expect inflation. I expect inflation to be 1%. So over the course of the loan, be it a year or 2 years or 5 years or 10 years, I expect the annual inflation rate to be 1%. Well, if I want a 2% real rate of return and I expect inflation to be 1%, in other words, I expect every dollar I loan out to lose 1% of its value every year, then I want to be compensated at an interest rate of 3%. Okay, so we can see here that the interest rate, I, is a function of the real rate of interest plus the expected inflation rate. So I is what we call the nominal interest rate. It's what's advertised. R is what we call the real interest rate. And this IP dot is called the expected inflation rate. Okay? Now you can reorient this. You could actually say that I minus the actual inflation rate equals the real rate. So let's suppose that the lender charges 3% on the loan, and let's just suppose that the actual inflation rate equals the expected inflation rate. Well, then what's the real rate of return? The real rate of return is 2%. If that inflation rate is lower than expected, say that prices don't go up at all, that inflation is 0, then the real rate of return would be 3%. Say that the inflation rate is 3%. Well, then the real rate of return would be 0%. So you can see that the expected inflation rate and the real rate of inflation can be two different things. And if P dot is let's do it this way. If P dot, the actual inflation rate is greater than the expected inflation rate, then what will be true? If this is true, then R will be what? Will be less than expected R. Okay? So if inflation is 3%, then R would be 0%. So what I'm trying to point out to you is the lender has to make some sort of guess about what inflation is. And the expected inflation rate is built into the interest rate. I'm just simply pointing out that the expected inflation rate and the actual inflation rate can be two different things. So if the actual inflation rate turns out to be less if the expected inflation rate turns out to be less than what the actual inflation rate is, then the real rate is going to be less than what was expected. Okay? All right, so we see that inflation is built into the interest rate calculation. And this is a very important idea. There's a third compensation that the lender expects, and that compensation is a compensation for risk. So another thing is built into the interest rate as well, and that's called risk. So there's a risk premium or a compensation for risk. So the risk premium is also built into the interest rate. So the interest rate is going to take care of three things again. It's going to take care of the opportunity cost, the right of losing, it's a payment for losing the right to spend the money now and enjoy the value now. The interest rate is also going to encompass a payment for inflation, and the interest rate is going to encompass a payment for risk. So let me give you an example again. I equals R plus E P dot. Let's say that the first person, the person who gets to borrow at 3%, remember what that was built upon, a real rate of 2% and an expected inflation rate of 1%. And maybe this is the interest rate that goes to a low risk borrower. But let's say that there's another borrower out there who's riskier. Riskier means less likely to repay the loan. The probability is higher the person will not be able to repay the loan. Well, in that case, I'm not going to charge them 2%. I'm going to want a higher real rate of return. I'm going to build in a risk premium. And so I'm still expecting 1% inflation, but I'm going to charge this borrower 5%, not 3%. So what's the risk premium? The risk premium, there's a 2% risk premium. And that's built into the real rate, which means it's going to get built into the nominal rate. So this is what we would call a higher risk borrower. So that's where risk enters the equation. So this equation here is very, very powerful. It summarizes a lot of the ideas that we want to talk about. Let me go ahead and move this down. And I'm going to rewrite I equals R plus E P dot. And where does opportunity cost enter the equation? Right there. The real rate of interest is a payment for the opportunity cost, giving up the right to enjoy value today. It's also a payment for risk. So we could call this default risk. And then this right here, the expected inflation rate, is the payment that's built in as the payment for inflation. So this is effectively a payment for what? For lost purchasing power. If money is going to lose value at a rate of 1% a year, I want that built into my interest rate. So inflation rate is a payment for lost purchasing power. So we can see how these three compensations are built into what we call the nominal interest rate. Okay. All right, now this is not a course on interest rates, rather this is a course on the time value of money. So we can see that an interest rate, the interest rate of 3%, which we used earlier, must encompass some sort of expectation about inflation, risk, and opportunity costs. So I'm going to assume here, just to keep this simple, I'm going to assume the rest of the way here that EP dot is equal to 0%. If EP dot is equal to 0%, then I equals R. So if the real rate of interest is 3%, then that equals the nominal rate of interest, okay? Because I'm assuming no inflation, okay? So we're going to leave inflation out of this, but we can see that it's easy to build inflation in. If you expect higher inflation, you build it into a higher interest rate. If you expect lower inflation, you build it into a lower interest rate. Okay, now what we want to do is we want to go back and talk a little bit about time value of money. I said earlier that if you take a present value and you multiply it by the interest rate factor, you get the equivalent future value. So we said $100 times what? Times 1.03 equals what? Equals 103. So $100 today, $100 today is equal to what? $103 a year from now, tomorrow, if the interest rate is 3% a year, if that's what lenders are demanding as payment for lost opportunity costs, lost purchasing power, and the possibility of default. Okay? Now let's talk about this interest rate factor for a minute. The interest rate factor is 1 plus r to the nth power. You know, what are you talking about? Well, r is the interest rate. So 1 plus 0.03, remember 3% is equal to 0.03. How many periods did we go out? We only went out one period. So this is 1.03 to the first power, which simply equals 1.03. Now, if we want to go out multiple periods, say 2 periods, then we have to increase the size of the exponent. So let's say, let's go down and just draw this up. Present value times interest rate factor equals what? Equals future value. So let's say a person has $100 today. They put it into some sort of account that earns 3% a year, but it earns 3% a year for 2 years. So it earns 3% a year over a 2-year period. Well, what is that going to equal? That's going to equal more than 103 because now we've gone out 2 periods. It's going to equal what? 106.09. You calculate that, that's 106.09. So here's what we're saying. We're saying $100 today equals what? $106 in 2 years if the interest rate is what? 3%. So this is 2 years in the what? In the future. Now let's do one that's very interesting here. What if let's just be really bizarre here. What if you wanted to know what $100 put in the bank today at 3% interest would equal in 100 years? Any idea what that would be? Well, I have a very fancy smancy calculator that helps me calculate such numbers. So I take 100 times 1.03 to the what? 100th power. And what do I get? I get $1,921.86. So if you put $100 into an account today, leave it there for 100 years at 3% interest, at the end of that time period you'd have $1,921.86. So we could say then that $100 today is the same as what? $1,921.86. How many years from now? 100 years from now. So this is today. This is when? This is 100 years from now. Assuming what? Assuming that R equals 3% a year, per year, per year. Okay? All right, now we're going to do one final thing here, and then we're going to wrap up this lesson, and then in our next lesson we'll actually be applying this to an investment problem. So let me just scoot this up. I want to show you another interesting side of this. If the present value times the interest rate factor equals the future value, we can rearrange this. We can divide both sides of this by what? We can divide both sides of this by the interest rate factor. Of course, if we do that, this cancels. The present value is equal to what? The future value divided by the interest rate factor. Okay? So if you know the future value and you know the interest rate factor, you can find the present value. Okay? So let's go ahead and let's do a couple examples like this and kind of get warmed up, because this is actually going to be a very useful tool when we look at investment decision making. Okay? So let's say that you need $100 in 1 year to buy something. So this is your future value. Let's say that you are going to put something, you want to put something in the bank today to have $100 a year from now, and this account, let's say, is paying 3% interest. So we're going to take it out to the first power. So the question is what would I need today to have $100 a year from now? This is future value divided by what? Interest rate factor. The question is what's the present value? What would I need today to have $100 a year from now at 3% interest? Well, if I do the division here, I'm going to get 9709. So if I have 9709 today, this is today, if I had 9709 today and I put it into an account earning 3% a year, I would have $100 1 year from now. This is my future value. So I can take a future value divided by the interest rate factor and get a present value. Now, of course, the further we push out the future payment, we push the future payment further and further out into the future, then the present value is going to be smaller. Let's check that out. So let's say you need $100 in 2 years. You need $100 in 2 years. The question is what would I need to put in the bank today at 3% interest? Well, if we're going out 2 years, this has to be to the second power. So what is this? This is actually going to be what? This is going to be 94.26. So if I put $94.26 in the bank today, this is what I'd have to have in hand today. This is my present value. I would have $100 when? 2 years. 2 years from now. In other words, the further I push out the future payment into the future, the less I need today to achieve that goal. Let's be silly here. Say that I want to have $100 in the bank 100 years from now. I'm really thinking about the future. I want to have $100 in the bank 100 years from now. Let's say the going interest rate is expected to be 3% a year. Well, to the 100th power, what would I have to put in the bank today? If my math is correct, I would have to only put $5.20 in the bank today. If I put $5.20 in the bank today, I would have $100 100 years from now. This is 100. 100 years from now. All right, so we see the time value of money. The further the payment is pushed into the future, the less its present value. That's the principle we want to get across at this point. All right, this is a good place to wrap up our little lesson, a very little lesson, but a very important lesson in finance in talking about the time value of money.